Okay, so let me start sharing. Okay, so we started talking about random vectors, and so you're given a bunch of random variables on the same probability space. You think of this as an ordered tuple, and therefore a vector, and we can define its joint distribution in terms of joint distribution function. I mean, in terms of uh, probabilities of the vector being less than or equal to a point where you think of the inequalities complementarities. And I said that they satisfy the following properties, that as you go to minus infinity in each coordinate, the joint CDF will be 0, and as you go to plus infinity in each coordinate, joint CDF will be 1. And Sudarshan asked a very nice question: what happens if any one of the coordinates goes to minus infinity? Then again the answer is 0, as I think Shubh Prakash argued in the response. So whenever you have such a question, think about this from first principles. We know we have talked about increasing and decreasing sequence of events. You know, you formulate it in that language and you will see what the answer is. Is there any non-trivial set that belongs? That's the kind of question you want to ask. And it satisfies the same kind of weak increase and right, and the analog of right continuity. Now the part D is something new. So it says that if you take one of the coordinates to infinity, then you get a CDF of the other. So this, of course, I'm just talking about two variables. I mean, this kind of thing generalizes in the obvious way. And I am going to skip the proof because it is by complete analogy with the case. So are there any questions about this statement of the theorem? Okay, so so let me give a definition here. So remember what fx is. Oops. Oh, sorry, I didn't say that. Okay, so let me define. So let fx of x, which is equal to the limit y tends to infinity of the joint distribution function, which is equal to the probability x less than or equal to x, be the marginal distribution. Be a marginal distribution function of fxy, and similarly for fy, which will be equal to the limit as x goes to infinity of fxy. Okay, so the term marginal is going to occur frequently. So what this means is that when I'm looking at a marginal on one variable, I'm completely ignoring the other variable, right? So so when we are performing this, when we are looking at these joint variables, I mean, I'm completely at liberty to forget about one. So maybe you do the experiment and you care about both x and y, but maybe I'm interested, from my point of view, I only care about x. So how do I extract that information? So suppose I'm given this joint distribution function. I don't care about y for whatever reason. I only care about x. So then how do I get out the information? I get it by looking at the limit y going to infinity, and then I get what is essentially the usual CDF, single variable CDF of the variable that I desire. Okay, the random variable that I want to look at. Okay, is this clear? So from a multivariate distribution function, I can get out the one variable distribution function by simply letting the all other variables go to infinity. Okay. So and this naturally generalizes. To random vectors of any dimension. As I said, you let the other n minus 1, if it's n dimensional, you let the other n minus 1 variables go to infinity. And we will see examples. Okay, so right, so all this is general blah blah about joint random variables, but as usual, we will specialize to discrete and continuous random variables, random vectors, just as we did earlier. And again, I will stick to the two variable definition, where this generalizes naturally. So the random vector xy is called jointly discrete. We will often not say jointly. If the range of xy is a countable subset of R2. Okay. In that case, there exists again a joint probability mass function P from R2 to 0, 1 given by P of xy is the probability that x equal to x and y equal to y. Okay. Again, I mean these are in complete analogy. Okay, so maybe I should in anticipation. So I'll write p xy, so, or maybe let me just leave it as p. Let me say here. So p xy, which is the same as p. So in case we need to specify variables, we will put them as subscripts. Okay, so this notation is a bit confusing because there will be subscripts and arguments which will be of the same shape. Just one will be lowercase and one will be uppercase. Okay, so let's do an example. And again, I'm going to do an example from the book. I'm just we'll go through it carefully. Okay, so this is what is the name of this? 4.3a. Okay, so there are 3 new, 4 used, and 5 faulty batteries. And 3 are chosen at random. X and Y are the number of new/used batteries. Okay. So the question is to find the joint PMF. PMF means probability distribution. Okay. So if you are given a question like this, so first you want to find the range of X and Y. They need not be the same. So you have to sometimes look carefully and interpret the question carefully. So what is range of X? So what values can X take? Somebody?
0, 1, 2, 3.
Correct. PF has answered. I don't know. PF. Okay. 0, 1, 2, 3. And what about Y? What is the range of Y? What are the possible values that you can take? Y can take?
Zero, 1, 2, 3, 4.
No. Okay, so I was worried that someone would say that. Okay. You're only choosing 3 batteries. So this is actually the same. You cannot have 4 because you're only choosing 3 batteries. But you can have any others. Okay, so therefore, X comma Y, when you look at this joint thing, so therefore, X comma Y lives in Ij, where both I and J run from 0 to 3. Okay, so that makes your life a little simple. Okay, so let me calculate one of them, or let me ask you to calculate one of them. So, I mean, I'm not going to do all 16 numbers, I mean, that's too much. But let's see how one would calculate. So what is the, let's do one example. So what is the probability that X equal to 1 and Y equal to 2? So how would you do this? I want someone to answer.
So this will be equal to P of 1, 2. P, small p 1, 2.
What is small p 1, 2? Yes, that's the definition, yes. No, I want you to give me what the number is. Yes, so this is exactly.
So that will be, sir, like 3C1 times 4C2.
Yes, 3 choose 1 times 4 choose 2.
Divided by total 5, 6, 12C3.
12 choose 3. I would actually, that's exactly right. Because you want to choose one battery from these 3, because you want X equal to 1. You have to choose 2 batteries from these 4, so that's 4 choose 2. And you also want to choose 0 from the other. It's good to keep this, because in this case 1 plus 2 is 3, the total number. But suppose I had, okay, so suppose I had something else, like X equal to 0, Y equal to 2, then I would have to do 5 choose 1. So this is 3 times 4 choose 2, so that is 4 times 3 by 2, and 5 choose 0, I'm not writing, that's just 1, and then I have 6 by 12, 11, 10. 6 is 6 because it's 3 factorial. So now I can do some cancellations. So 6 goes here, 2 and 2 cancel 4, and and so I get 9 by 110. So in your book, this book answer is written as 18 by 220. They, for some reason, like to keep the common denominator as 220. Right. So like that, you can calculate all the numbers, and fortunately, I have Mathematica to do it for me. So this is how the general formula looks like. So maybe I should have said that. So Pij, which is the probability that x equal to I, y equal to j, will be 3 choose I, 4 choose j, 5 choose 3 minus I minus j. This 3 is not this 3. This 3 is the total number of batteries chosen divided by 12 choose 3. Okay. And so I enter that here. I plot this table. I don't know if you can see. Maybe I'll make it larger. So this is how this table is going to look like. And this 9 by 110 is what we just calculated. Okay. Because x equal to 1, so this is starting with 0. So the first row, and 0, 1, 2, second, third column, 2th column. Okay. So like that you can calculate all these numbers. So I'll come back to this example next. Okay, is that clear? Any questions about this example? Okay. Okay, so now just like you have the marginal distribution functions for a discrete random variable, you can talk about the marginal PMFs. So the marginal, so the marginal PMF is what it is. So we will write it as a definition. The marginal probability mass function of x in the random vector xy is given by px of x is the probability that x equal to x. Right? So this is just as before, as in the marginal distribution function, is just ignoring y completely. Okay, so it's the marginal PMF of x. So here is an exercise for you. Marginal PMF is given by Px of x is the sum over all y of Pxy. Right? So just like we take the limit here to get the marginal distribution, marginal CDF. Right, cumulative here in parentheses. Just like that, you sum over all y. Okay, so this I leave it for you as an exercise. And let us compute the marginal CDFs in this case. So let me call this table something. So t equal to that. Okay, so that's t. And now what I will do is I will sum t of 1 and sorry. So maybe I'll use j here. So j unfortunately I have to shift indices. Okay, so what this says is this is the first row now. So I mean, this is an unfortunate convention that the row and column indices start with 1, whereas we are our i's and j's start with 0. Okay, so for the first row, if you sum these things, I claim you'll get 21 by 55, and now I can so I get all the marginal PMF. I get the marginal PMF of the first variable by summing over the j. Okay, so here, so when x equal to 3, which is this one, there's only one thing to sum, and that is here. And if you sum these two, you get 27 by 220. And if you sum these three, you get, and you can check that this, we'll check in a second that this sums to 1. And I can also do similarly the marginal PMF of y. In this case, I will take the same sum, I take the same quantity, but I'll sum over I, and I'll do this for fixed j. So now, when j equal to 1, I'm summing this column, I get 14 by 55, j equals to, I get 28 by 55, etc. And this last column, sanity check, is that you get exactly this 1 by 55, because the others are 0. Okay, and now I can check. So maybe I'll do that check over here. I check that if I sum both I and j over all these, I get as it should be. So just to forewarn you, this kind of distribution has a name, and it will occur. This will be one of the examples we will see later. Any questions about this example? Okay. So that's good. So we have the we saw one example of a joint discrete random variable. So now it's natural to talk about a joint continuous random variable. The random variable, or random vector, sorry, xy is called, again, jointly continuous if there exists, again, the analogy is quite clear, an integrable function f sub xy, which I will call f for now. Let me write it on the next line. fxy is f from R2 to R plus, such that the joint CDF is given by fxy of xy is the integral from minus infinity to x du, integral minus infinity to y dv, oops, FUV. In that case, f is called joint probability density function, or density in short. We won't have to say joint usually, because it will be clear from our context whether this is random vector or random variable. But yeah, we will say that. Okay. So before we do an example, let me ask you the following. So if I have the joint density, I can get out the joint CDF by integrating. How do I get the, how do I do the converse? How do I get the density, joint density from the joint CDF?
By taking the partial derivatives.
Very good. Which partial derivative?
So first with respect to u and then with respect to v. I mean, first with respect to x, then y.
Right. So it's x. That's correct. So it's the mixed partial derivative. So the joint density is given by. So f xy is d2 of f capital F with respect to x and y. So you have to take the mixed partial derivative. Okay. Okay, so let's do an example, and this is really nice historical example. So this is called Buffon's needle. So it's a real, it's a physical problem, and the answer is surprising, or should be surprising, if you have not seen it before. Okay, so consider a plane with lines drawn at y equal to n for all integers n. So you think of R2. Oops. Maybe I can do this. And you draw lines equally spaced, just for convention. So this is let's say y equal to 0, y equal to 1. Okay, I'm horrible at drawing as usual. You can see they're not equally spaced, but whatever. You get the idea. Okay, so you have this line. I've just drawn the x-axis for y-axis just for convenience. Just okay. So now a needle of unit length is dropped randomly. So I'll describe what randomly means in a minute. So find the probability that the needle intersects a line. Okay, so you have a needle. Okay, it's not the color, and it's the same length as distances between consecutive lines. So the needle could fall like that, or like that, or, no, or I mean, it could in principle fall exactly like that. In which case we have to agree on a convention of whether we say it intersects or not. But that's the question. Is the question clear? You drop the needle randomly, and you want to find the probability that it intersects a line. Okay, any line. Okay. So let me first describe the, well, okay. To describe the random assumptions, I need to set some notation. Okay, so let capital X, capital Y be the center of mass of the needle. Okay, so it's halfway between. Okay, and capital theta be the angle with respect to the x-axis. So these are random variables. Right? So x, y, and theta are random variables. And now let z be the fractional part of y, which by definition is y minus floor of y, which some of you might have seen as box y. It's the greatest integer function. That's the okay. Oh, sorry, there should be floor. So this is called the floor. The reason one doesn't like this notation because there's one often wants the ceiling also, which is the smallest integer greater than or equal to y, and so on. So it's better to distinguish the two. So we use floor function to say this. Okay. Now I can state my assumptions. So assumptions about the randomness. So what do you think? What can you say about, or what are natural assumptions about z and theta when we say dropping randomly? Does anybody have a guess? So z is the position. So when we say z, so this is z over here. So when I'm talking about z, I can sort of ignore where on this along the y-axis it sits. I mean, I can say that it's placed around this region between y equal to 0 and minus 1. Between y equal to plus 1 and minus 1, because everywhere else it's going to be kind of the same. Okay, so that's the point of choosing this. So what do you think we can say about z? Anyone wants to volunteer? What is a reasonable assumption?
So it can be anywhere between 0 and half.
No, why just 0 and half? I mean, can't it be between half and 1? I mean, this is the fractional part, no? So the fractional part of 1.7 would be 0.7, no? Why can't it be between half and 1?
So then it would lie anywhere between 0 and 1.
Correct. So what does lie? Okay, very good. So that's the first step. So it will lie anywhere between 0 and 1. But I want to make specific assumptions about the randomness.
So every point between 0 and 1 is equally likely, or every interval.
Yes, so what's the name for that? Yes, very good. We have given a name to such things.
Uniform.
Yes, uniform in what?
So uniform in 0 to 1.
That's right. So the first assumption is that Z is a uniform 0, 1 random variable. Okay, which means This is continuous. So which means its marginal density is 1 for 0 less than equal to z less than equal to 1 and 0 outside. Right? This is the density of the uniform 0, 1 random variable. Okay. So that means you're not privileging where you're going to place. You're kind of closing your eyes and placing the center of mass anywhere on this. I mean, we don't care so much about the x position. So let's just look at the y position. This is tantamount to saying that you don't privilege any particular position on the y-axis as you on this place. Okay. All right. What about theta? So let me maybe draw a picture here to clarify. So let's say this is my needle. So this is my x-axis and this is capital theta. Okay, so this is the center of mass. This is z. Okay, so what are you assuming about theta? Or what is a natural assumption? I mean, you can take anything, but
so it would lie between 0 and pi, both inclusive. I mean, 1 inclusive, 0.
That's right. So okay, and so that's about the range of theta. That's absolutely right. What about the nature of the uniform? Nature of the randomness.
So again, it would be uniform between.
Yeah, that's right. So I gave the answer away by mistake. Okay, yes, that's right. So again, it's natural to suppose that theta is uniform between 0 and pi. Again, open, closed, I don't care so much. So its marginal density, f theta of theta, is 1 by pi for 0 less than equal to theta less than equal to pi. Right? So we are assuming that, so now what am I saying? The orientation, this orientation of the needle, I don't sort of privilege one orientation over the other. Okay. So I'm agnostic with respect to the orientation. So the first says I don't care where it is translationally, and the second says I don't care where it is rotationally. Right. So I am as ignorant as possible about both of these. Okay. When I close my eyes, I have no idea either of the position or the orientation of the plane. But I need one more assumption, and this is this is a little more subtle, but you will appreciate this maybe soon. I need to say that the joint density f capital Z capital theta of small z small theta is the product of these. That is to say, my choice of translational location does not influence my orientation or vice versa. Okay. So in other words, these two are kind of decoupled. Okay. So is this point clear? I mean, this is maybe a little subtle. I mean, in principle, these two could talk to each other. But we are saying that we want, or we believe a natural assumption of randomness is that these two are decoupled. Okay. Is there any questions, please? Okay, so now, so what this says is this coupled, so therefore z theta belongs to the rectangle 0, 1 cross 0 pi with density this equal to 1 by 3 constant. Okay, this is a constant density. Okay, so now let's try to interpret what intersection means. So I mean, so this is what we want. What does intersection mean in this language? So intersection occurs if what? So we have to say something about. So I mean. So this is a rectangle. So this is 0, 1 here, 0 pi here. I mean, okay, my scales are all messed up. But now I want to say on which points here do you get intersection, or which region do you get intersection? Right? So that's what. So let's analyze that a little carefully. So let me draw the needle again. So here is Z. Okay, so let me draw the two successive lines over here. And so sorry about that. This is theta, and this where is it? That this is Z. Right. So these are two consecutive lines, whatever y equal to n, y equal to n plus 1. And this is Z, this is the location of Z, this is the center of mass, and this is the angle, random angle theta. So what conditions can you say? Under what relationship between Z and theta will you have intersection? Anybody?
Sir,
Yes.
if z is more than 1 by 2, then sine theta by 2 it must be more than 1 minus z.
Sorry, why do you have sine theta by 2?
So because half
when
of
you
it
say
must...
when you say sine theta by 2, do you mean sine of theta by 2, the angle, or sine theta divided by 2?
No, sine theta divided by 2.
Okay, so what is the relationship?
So if z is more than 1 by 2, then sine theta divided by 2 must be more than 1 minus z.
But I don't want to make any assumptions about z being more than 1 by 2 or less than 1 by 2. But you are on the right track. Can you say that again? So you have sine theta by 2. So let me write what you said. So sine theta by 2. And
More
what?
than. If z is more than 1 by 2, then this should be more than 1 minus z.
Sine theta by 2 should be more than 1 minus z.
Yes.
But you are saying if z is less than 1 by 2. But why do I need
more than 1 by 2?
More than 1 by 2. Why do I need to make that assumption?
So because in which part of it does the needle intersect? At y equals to n plus 1 or y equals to n? Determining that.
Right. So maybe I should have drawn it like this. I mean, remember that it can only intersect one place because this needle has length 1 and the distance between this is also length 1. So, I mean, I think you're right, but you're missing the point that there is no reason to assume that z is more than 1 by 2.
So If we make another condition for z is less than 1/2, then
No,
sin
there
theta
are,
by
that's right, that's right. So Purnendu, you're absolutely right, but that's a union of things, union of events. In this case, the intersection is on top. This is 1 minus z, right? And this is half sine theta, right? And you are saying that 1 minus z is less than or equal to, not this, sorry. 1 minus z is less than or equal to half sine theta, right? That is correct. But you don't have to assume that z is greater than or equal to half for this, right? So this is intersection on top. So one way intersection can happen is if it happens on top, and that's exactly this condition, or what's the other condition? I mean, okay, so my figure is a little messed up, but this is the center of mass. Okay, never mind, but you get the idea. So this thing is again half sine theta. Sorry, my figures are terrible. And intersection will happen on the bottom if z is less than or equal to half sine theta. In other words, it extends on this side. Right? So both can occur, and I don't need to make any assumptions on z being greater than or equal to half. Yes, Soham?
So it could be that z and theta, like z comma theta, belongs to the closed interval 0, 1 Cartesian product with open interval 0, pi. All such points satisfy the criterion.
That would be everything.
Yes, sir, but
No, but then you're saying it will happen with probability 1. I mean, that's certainly not true. I can have things very close at angles very close to 0. Right? So that what you're saying is certainly not true. But I'm saying that Purnendu is correct, except that you don't need to assume that z is greater than half for the first condition and less than half for the second. Okay? If it comes automatically. I don't have to bother. Okay? Okay, so please ask if there are any questions. So let B be the set of all z theta such that z is less than or equal to half sine theta, or 1 minus z is greater than or is less than or equal to half sine theta. And we want to calculate probability of B. So thus the desired probability of intersection is the probability of B, which is the double integral d theta integral dz over B of f z theta of z theta. Okay, so now let's do this calculation. Now it's a matter of doing your calculation carefully. So the joint density is just a constant, so we don't care so much about it. Now the issue is that the limits are tricky. The issue is not with the integrand, the issue is with the limits. So I claim it's natural to do the pi integral first, outside, sorry. So I have 1 by pi integral 0 to pi d theta, and now I'll do the z integral. So there are two integrals. This one is lower limit for z, so z goes from 0 to half sine theta dz. It's just one, there's nothing else here, plus this is a lower bound from the other side. So it's 1 minus half sine theta to 1 dz over here. Okay. And now you can do this integral. So it's 1 by pi integral 0 to pi d theta. This integral just gives me half sine theta, and this gives me 1 minus 1 minus half sine theta. So okay, half sine theta plus 1 minus half sine theta. The ones cancel, and so I get integral 1 by pi 0 to pi d theta of half sine theta plus half sine theta, which is sine theta, and this is minus cos theta 1 by pi from 0 to pi, and this is exactly, so I'll get minus 1 minus 1, so that's 2, so I'll get 2 by pi. Okay. So what I would like you to appreciate is that from a problem which has nothing to do with circles or anything, this is a probability question about a needle which is a straight line intersecting lines. I mean, there are only straight lines in this problem, but somehow you get out pi in the answer. So this is one of the things that Buffon noticed. So you can compute in principle pi this way. In principle. But the problem is, so this is exclamation mark, because this is a highly non-trivial statement. If without this computation, you might not have believed that. But the problem is that this is a very slow algorithm for computing pi. Okay, you have to do a sort of very high number, like 1,000,000 times you have to drop this to get like 3 decimal places or something. That's the problem. Okay. So yeah, this is one of the things that Buffon is famous for. And you can read about it on Wikipedia. There's more general problem about if the length of the needle is L and the width between strips is T, then you get a more general answer which involves L by T. Okay. All right. So I'm running out of time. Okay. So let me just like I gave you this exercise for computing the marginal PMF, I can also give you an exercise to calculate the marginal densities. No, but before that, let me define them. So so if xy is a continuous random vector with density, that is joint PDF fxy of xy, the marginal density functions let's just say function of x is given by f sub x of x, which is integral minus infinity to infinity fxy of xy dy. Okay, and similarly for x. And this is in complete analogy with the marginal PMF that I showed earlier. Okay, so just like you take the sum here, you take the integral here over the other variable, and similarly for y. And I leave it for you as an exercise to relate the marginal density and the marginal CDF. So the marginal CDF of x in this case is given by fx of x is the integral from minus infinity to x of fx u. Okay. So this you can just go by definition and of the marginal CDF and see how it relates to the marginal density. So you use the double integral, again reduce it to a single integral, etc. Okay. All right. So I think I will stop here. Are there any questions? Okay. Then let me stop recording.